Hi there, and welcome to video 2. So, in adhering to the ALARA rules, you can see I've removed the radioactive plate behind me. And what we're going to talk about in this video is how to extract data from the detector. So there's essentially 3 ways that you can do this. The first and most obvious, I suppose, is simply reading off the detector rate from the OLED screen. If you require event-by-event information, so if you want to know what that actual pulse of light was actually saying, that data is saved directly to an SD card down here. So once I reset the detector, after introducing itself, it tells me that it's creating file m018.txt, so that counts sequentially upwards. And in that file, you'll find event-by-event information that can easily be read into a C++ or Python-based application, an example of which I provide in the GitHub repository. Okay, the third way to record data is directly through a serial connection to your computer. So if I was to plug this directly into my computer, I can read the information that is streaming out of the detector through this cable. There's various benefits to having either the data recorded to an SD card, say for example you want to record it while you're on an airplane flight, or through the serial connection to your computer. Say you want to measure the precise rate over the course of 11 years to look for the solar cycle, the cosmic ray muon correlation with the solar cycle. Well, you might not want to rely on the SD card for that. You might want to record that directly to a dedicated PC or something like that. And so we provide functionality for that as well. So I'm going to show you how to do all these in this video. So let's get started. Great, okay, so now that I took my micro SD card, I've inserted it into my computer. I can open up my SD card, and I see that there's a file called file C001. What this file is telling you is that it was taken in coincident mode. That's the C here. M would mean that there was no coincident detector attached. And then this number here just counts sequentially upwards as you reset the detector. Every time the detector is reset, a new file is created. So I'm going to take this file and put it on my desktop. Now what I'm going to do is I'm going to go and get the example IPython notebook. This is found in the GitHub repository, so you probably have already downloaded the GitHub repository, but if not, you can type in CosmicWatch into github.com. A couple ones pop up, and you go down to CosmicWatch version 3, and we're going to hit this green button here and download the repository. There it is here on my desktop. And now if I look inside this folder, you can see that in the plotting folder, there's an example IPython notebook. And this example IPython notebook is what I'm going to use to make a couple plots from the data. Great, so I'm just going to move my data over into this folder just for now to make it simpler in one more step. If I open up the data, I'll just show you what data looks like. What you can see inside the data is there's first a header that describes sort of the run condition, when it was launched, what the detector's name was. And then here it describes what each column of data actually represents. So the first number is the event number. So each row here is a different event, okay? And each column represents a different property of that event. So event 1 happened at 9:03 p.m. On September 16th, 2020. This next column here indicates the time taken since startup on the teensy. So this happened 263 milliseconds after starting. These two numbers here are actual measurements from the detector in ADC counts. This probably isn't going to be useful to you, but this next number here, the SIPM voltage, this is the peak voltage of the SIPM pulse. So remember on the previous video, the SIPM pulse, it was this fast rise sign, exponential decay. This number is supposed to be roughly what that upper voltage actually is. This event happened at a temperature of 26.9 Celsius with a barometric pressure of 102,006 HPA. And then this second last column is the detector dead time between each event. So from the start of the detector to when this particular event was triggered, there was 50 milliseconds of dead time. And so what happened here, I can tell you what happened here is the screen updated. The screen, to run the OLED screen, we actually had to stop making a measurement for 50 milliseconds to update what the screen is reading out. And this is a generic thing with many particle detectors. As it's doing some calculation, it's unable to make a measurement. And when it's unable to make a measurement, that time is called dead. It's dead time. And so what we have to do is we have to actually make sure that we do not or make sure that we account for the time in which the detector was dead and unable to make a measurement. This very last column is whether or not this event was coincident with another detector. And you can see event 3 was a coincident event. So this was a muon. This is a muon. I can see there's another muon down here. All these other ones are likely not muon events. So this is some example data, and let's just make up some plots of it now. Okay, so the next step is I want to launch IPython. So on my desktop, if I type in IPython 2 for me notebook, sorry, this is written in Python 2. You might just have to type in IPython notebook, not IPython 2 notebook. I open up this folder on my desktop. I go to plotting and example notebook. Here is the example notebook for the detector. Okay, so there's some description on how to run it. First, the first cell here just basically tells you, here's the repository and the YouTube videos that you're watching right now. Then there's requirements for running this script. So this script is pretty simple. It essentially just requires the simplest programs to make plots using Python, so matplotlib or pylab, scipy, numpy. All these are contained in Anaconda. And so I just download Anaconda, and the script worked fine for me. Yours might be slightly different. You might have to do sudo to get admin privileges to install this. I'm going to have to leave this part to you. Here's a description of what this particular IPython notebook does, and it's very simple. You essentially there's going to be something called a CW class. You just input your file location. For us, it's going to be file, inside the desktop, inside this folder, it's going to be file C001. Specify what sort of binning size I want. So I'm going to bin the data by 120 nanoseconds, and that's all. Then you have access to all the data in that file. So here I'm just going to import, here I'm just importing numpy, whatever. This first cell is just imports. I'm going to skip that. Here's where I'm defining what CW class is, and we'll just give that, I'm just going to skip that cell too for a second. In this cell here, I'm actually going to take that file. So that file was called file C001. Okay. And how about I bin it in 120, how about I bin it in 240 nanoseconds? 240 seconds, sorry. So each bin, if I was to plot rate as a function of time, each rate measurement is going to contain 240 seconds. If I hit Shift-Enter, it loads that file. And you can see here, if I wanted to get, say, the average temperature from that file, if I type in that file, so the CW class is assigned to this variable f1. If I simply type f1.temperature, and I can just tab complete even, and then Shift-Enter, it gives me an array of temperature values for this particular measurement, for this particular run. Each one of these is a different event. I could also go SIPM, and here is an array of the SIPM values, or I could go pressure HPA, and here is an array of pressure values. So this gives you access to all the data that's contained in that file. So let's just get rid of this guy. All right, then I provide some example functions to make plots like a rate measurement, or if you want to make a histogram or something. So this first one is just called nplot, and it's just a rate measurement. So here, I'm not going to go through this. You can read. I tried commenting this sufficiently so that you know how to use it. Essentially what I'm doing here is I'm plotting x, or time. So x, I'm going to do bin time versus count rate. Okay, so bin time versus count rate. I hit Shift-Enter. You can see the axes are kind of too small here. It's because I actually have to rerun this first cell. Let's run that again. There we go. Okay, so what I'm plotting here is I'm plotting the bin time versus the count rate for muons, and the bin time versus the count rates for non-coincident events. I'm also specifying the error here, which is just a statistical error, and what color I want to actually make the plot in. There's also the labels for each of these. If I want to auto scale, or if I want to scale manually from 0 to 6, whatever I'd like. The figure size, perhaps I want to plot a wider image. I can just change the figure size to a larger x value, or the y dimension if I'd like. There's also, I can change this to a log scale. So rather than plot rate as a function of time in linear scale, I could make the x scale maybe log. Let me just change this to 1 just in case. Oops, where'd it go? Okay, now it's a log plot, which is a very weird representation for this particular data. But anyway, so this gives you, so this particular function is a nice, easy way to modify these particular plots that I've pre-made for you. Anyways, what this data is showing you is the non-coincident event rate in that file as a function of time, as well as the coincident event rate as a function of time in red. I'm going to just change this back to linear. This log scale looks a bit funny. Great. Okay. And let's say you wanted to change the binning. Let's say there's too much statistical fluctuations here and you want to bin it in larger chunks. Maybe you want to bin it into 10-minute chunks. If I go back to my data up here, where I defined F1, how about I bin that in 600-second chunks? So that's 10 minutes. Let it load. Now if I go back and make this plot again, you can see the statistical fluctuations are lower. That's because each one of these data points represents 10 minutes of data. Okay? So here is the non-muon rate, here is the muon rate. Great. You can also plot very simply, the pressure and temperature. That's what this particular example does. So over the course of this measurement, the pressure started off at about 1020 HPA and then decreased to about 1018. Here is the temperature where the measurement was made. I see that the temperature increased quite a lot at the beginning of the measurement, then slowly decreased over, I'm guessing this is overnight. There's also, let's say you wanted to make an example histogram. So let's just get that. So here in hist, I specify the data that I want histogram as maybe the SIPM voltage. Maybe the SIPM voltage, and I only want muons. That's what this is doing. This is called a mask here. You can read about it up here. And so I'm going to plot the SIPM voltage for the full data set, the SIPM voltage for just the non-muons, and the SIPM voltage for just the muons. And I'm going to all these histograms will be superimposed on each other. Here I can change the color of the histogram and so on. Shift Enter. And there is a nice plot, histogram plot of that particular data set. So what this particular set is telling you is that let's say I look at all the events. So all the events are, this dark black histogram in the back here. There's quite a bit of structure here. Some of the structure is due to electronics. Some of the structure is due to actual features in the background spectrum. And but most notably, what I want to point out here is when I now compare all events to just coincident events, you can see the coincident events are much lower in this region here. However, they're comparable in size to the non-coincident events, above maybe 35, 40 millivolts. And so what this is saying is the coincident events have larger SIPM pulses than the non-coincident events. Non-coincident events are these yellow guys down here. That means that if you were to just look at the pulse height, let's say you just extracted all events that had a pulse height larger than, say, 40 millivolts, half of those would have been probably caused by muons. And that's what this histogram is kind of telling you. So like I mentioned at the beginning of this video, there's a third way to record data. And this is directly to your computer using the import data.py script. So if you run that script with Python, you can record data directly from the detectors. So this is beneficial if you have, say, like an Ethernet hub, and you want to record multiple detectors through a single cable to your computer. So here I've connected 2 detectors. For this example, I'll actually use 4 detectors. Plugged into the Ethernet hub. The data for every trigger flows out through the cable and into the Ethernet hub, and then the import data.py script sort of in a round-robin fashion asks each detector whether or not it saw an event. So the only issue with taking data in this way is that the transmission time of the data is on the order of milliseconds. There's a finite amount of information that the detector can send to your computer per unit time. And therefore, if you were to actually look for coincident events like this, they will be offset by order millisecond. And we'll see that in this example. So what I'm going to do is I'm going to plug in another 2 detectors, and I'll give an example of this. Great, so we now have 4 detectors communicating independently through this USB hub directly into my MacBook Pro. None of them are connected through the coincidence cable, and all the data from each one of these detectors is now flowing in through a single USB cable. If I open up the GitHub repository that I just downloaded, you can see there's this recording data folder and the script called import data.py. We're going to use this to record the raw data from these detectors directly into a single file. So in my terminal here, if I show you where I'm located in the recording data folder. and you can see there's this import data.py script. If I run that, Python import data.py, it asks me what would I like to do, and right now the only option is record data directly to the computer. So I hit 1. Now it says, it looks through all the serial ports, and it says which one of these ports is your detectors. So my Bluetooth, I'm not talking through Bluetooth to the detectors. I recognize that these 4 communication lines here are my 4 CosmicWatch detectors. So I type 2, 3, 4, 5, and then hit enter. And now it asks me where I would like to save the data. So it gives me the default location as the location where the script is being run, with the default folder name called CW data. And I'm just going to hit enter and save it into the default location. So if I give it a second, it should create a file. Yeah, there we go. It creates a file called cw.data. And let me just give it a second to populate that file. So data is now flowing into this file. If I open it up, here is some data. And you can see right now the events don't come in sequentially, right? Because they're coming in from different detectors. So there's an additional column here at the very end that actually tells you which detector was talking to it. So I have a detector here called Victor Hess. And so for this event came from detector Victor Hess, which I don't know which one in the stack it is, but it's one of these here. So what I can do now is, since there's no coincidence cable, none of these coincident events will be, but none of these values here will be coincident events labeled with 1. Instead, I can look through the timestamp over here for coincident events by I, or with the computer program. So this timestamp has been replaced with the computer timestamp. So as data is flowing into the it's flowing into my computer tells or records the time that that data came in. And now I'm going to look for data that came in at roughly the same time, within maybe a couple milliseconds, 2 milliseconds. So let me just close out here and reload it so I get a bigger data set. Okay. And now I'm just going to scroll down, maybe I'll scroll down somewhere here. And now what I'm looking for is events that came in roughly in coincidence. So I can see right here, so these two events, for example, detector from Bruno Rossi and Richard Feynman, these events came in at almost the identical times, except they were 9 milliseconds apart, you can see. So that is a good candidate for a coincident event right there. So here, you would have to define what sort of time window you would consider a coincident event. Would you consider a 9 millisecond coincident? Normally you would say no. However, the serial communication time is very limited. And so the speed at which it's talking to these detectors is relatively slow. I would say anywhere from like a few milliseconds should be expected between measurements. So although the coincident cable is able to identify coincident events with a time window of a few hundred nanoseconds, maybe a few microseconds, this way of communicating can only detect, has a time window. You have to implement your own time window, and it has to be order millisecond. So if I look down here, maybe at this event here, which was Frank Wilczek and Richard Feynman, they triggered, and you can see that they triggered within 1 millisecond of each other, that one and that one. So I would argue that that was definitely a cosmic ray going through the detectors. And I can see that one of these events was very, very bright, 100 millivolts. So that was a very bright pulse, which, you know, as we described earlier, is likely a muon. This one was not very bright, but I would still say that this was a coincident event, and I would say that this is actually a coincident event. And actually, you know what, if I look a little bit higher, one event higher, so if I look at these 3 events here, so Victor Hess also fired at that exact same time, 1 millisecond prior to it. And so I would say that these 3 events came in coincidence with each other. So 3 of these detectors fired at the same time and sent their data to my computer. Anyways, this code is still in the works. It'll be available on the GitHub for you to play with if you like. It's written in Python 2, but I'm trying to make it so that it works with Python 3 as well. By far the easiest way to record data is through the SD card. However, if you require something like this, some solution like this, I'm trying to provide the tools available for you to use it. So that's going to end this video. We'll talk to you in the next one. Great, that wraps up video 2. I'll see you on the next video. Thanks very much.